All right, recording is rolling. Welcome to Wednesday, April 12th. So we're going to do Kahoot circuits today. You guys remember yesterday I gave you guys this packet of conceptual questions. The first page front and back were on current, and the second page front and back is on circuits, which is what we're doing today. Okay. Tomorrow I'll do some more review with you guys, do some circuits, go through circuits, Kirchhoff's rules, the whole deal, review. Okay. And then on Friday, there's going to be a quiz. Now, the quiz, most of the questions are going to be in the packet that you have in front of you right now. Right? So just follow along. Right? Oh, did I say open notes? I say open notes, right? Reiterate that. Okay. And then I've also got a circuit on there. And then when you guys follow with tomorrow's review, I think if you're able to follow what's going on, then you'll be good there too. Right? Are you guys ready to go? All right, so switch screen. All right. Right. No, yeah, so thank you everybody for hopping on there. Right. Yeah. And start. In order to form an electric circuit. Right, you need all those things. Right? So some kind of power source, you might say a voltage source, for example. Right? You need a complete path for the circuit. Right, it needs to go from the positive to the negative terminal, or negative positive, however you think of it. Right? And yeah, ideally you do want some kind of resistor also. Right, like if you don't have any resistance, you call that a short, and that's not a good scenario for usually. Okay, right, so all the above. Right. Yeah. All right, points on the board. In order for current to flow, all right, nice. There we got it. Yeah, complete path for the circuit. Okay. That's also called a closed circuit. Closed circuit. Okay. If the switch is open, that's like hitting the off switch, right, which would break open the circuit, and you wouldn't have a complete path for electricity flow. All right, all right. Electrical resistance is measured in ohms. There you go. Right. If you said joules, guys, what does joules measure? Energy. Yeah, joules is energy for work. Right. Volts, of course, is like some kind of voltage or potential difference, you could say. What does amperes measure? Current, right? Amperes measures current, right? Yeah, but ohms is, let's go here. Right, yeah, ohms is resistance. There we go. A closed circuit is a circuit in which charge can flow. Yeah, charge can flow. I do want to switch over and show you guys pictures of this. Okay? So you guys are all these electricity posters hanging around my room. Okay, so I got a flashlight schematic. Okay, voltage source, there's battery, resistor, could be a light bulb. Okay, and oh, look at the switch here. Okay, now if the switch actually is in this position, that would make that an open circuit, right? Because the electricity can't flow back to the battery. The current can't flow back. Right? But if you were to close this, like, right, then you would have a closed circuit. Electricity could flow. Closed circuit. Yeah. Nice job. You guys are getting these. When two bulbs are in series, the oh, all right. So a little tough one there. Okay. So in series, so one after another, hooked up sequentially. Yeah, it is always the same current that flows through each bulb. Okay. So they flip over and remind you guys how this works. Actually, here I'll come back to that one. Let's do like the simple version here. Okay. which is my waterfall model. You guys remember this waterfall model? Okay. Analogy. So here's voltage source, and you got three resistors in series, right? Remember Paul Hewitt was hooking these up, and every time he added one, they got dimmer, 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 right? Well, okay, you guys did it too. Gave you guys Christmas slides, right? But it's the same current everywhere, even if they're different resistors, even if it's like 5 ohms and 10 ohms and 20 ohms, right? Doesn't matter. It could be like 3 amps, 3 amps, 3 amps. It's got to be the same number of amps everywhere, right? Same like gallons per minute, sort of. Okay, now the rule that this goes along with, well, I did redesign this and like retitle it a bit, but it's basically this right here, right? The current is the same everywhere, right? Even if the resistors are different, that's okay. It's the same current everywhere, right? Right, everybody good so far? Ah, I've got Natalia on fire, Kahoot King, Haley, oh, and Ashlyn. The symbol used to represent resistance in a schematic diagram. Zigzag. Here you go, zigzag. Hmm? On fire. To the top. When resistors are put in series next to each other, the overall resistance uh, will, yeah, get larger, will increase, right? That's this, uh, that's this right here, right? You guys remember that? Okay, so if they're in series, just very simply add them up. In series, you just very simply add them up. Okay, you guys do that? Okay. Ashlyn, back to the top. When resistors are put in parallel, what happens to the overall resistance? Uh, oh, nice, nice, nice. Almost everybody got that. Okay. So, remind you guys, that works. And so resistors in parallel, you can use this reciprocal method to figure out the total resistance. Right? If you're only working with two in parallel at a time, you can do product over sum, right? Lead to the same outcome for two anyway, right? And there's an analogy that I've been using with this was like if you have a team of people working in parallel on a project, like painting a fence, right? So every time you add on a team member painting a fence, the overall time to paint the fence decreases, right? So same thing, resistors in parallel. It's the same math. You guys are knocking these out. As more lamps are put in a series circuit, the overall current. Oh, all right. That was a little tougher than that was going to be. It's okay. This is actually like a two-part question you have to think about this in terms of. Guys, as you put more and more in series, what happens to the overall resistance? The overall resistance. That would increase, right? Right? Like every time you add on another resistor in series, the resistance goes up, the overall resistance from the battery's point of view, right? Then you have to flip back to Ohm's law. Ohm's law. You guys remember this? Okay. So if the resistance is going up, 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 the current must be going down, at least for the same voltage source. That would have to be true, right? More lamps put into parallel, the overall current yeah, would increase, right? So that's like the opposite thing, right? Because you put more and more in parallel, that decreases the overall resistance, right? Just like working on a team project, or team member decreases the time for the project. Therefore, back to Ohm's law, less resistance means more current. All right. Compared to resistance of two resistors in series, the same two resistors in parallel. Would be less. Okay, most of you guys got that. We flip over and just for completion, okay, gave you guys a numerical example on this. So it says 10 ohms and 10 ohms, right? The resistance total, well, they're in series, right? One after another, has to be 20 ohms. You just add them up, right? But if it was parallel, it would look more like this. Right? 10 ohms, 10 ohms, look like that, wouldn't it? Right? And then the resistance total would be product over sum, 10 times 10 over 10 plus 10 ohms. That's like 100 on 20. That's only 5 ohms. Hey, that goes hand in hand with the story of 10 hours painted fence, 10 hours painted fence, team up. Now it's only 5 hours. Right? All right. So the resistance drops in parallel. When one bulb in a series circuit burns out, containing several bulbs burns out, oh, right. None of the other bulbs will light up. Okay, so we're talking about series. One burns out. Okay. Oh yeah, give you guys the visual on that. Possibly. Um, Ah, yeah. Okay, that's probably like something like that. Yeah, I've seen like different brands of Christmas lights. So yeah, some of them you break one bulb and the others still light. So that's more like a parallel setup. But you're right. You're right. If you break a bulb and then they all turn off, yeah, that would be like this right here. Like some do a series. So probably different manufacturers put them together different ways. Right? Yeah. Right. So we got a whole circuit. Current goes through one at a time. But yeah, if you like burn this guy out, that would open the circuit, and now no electricity is going to flow at all. Right. So we're talking about. When one bulb in a parallel circuit burns out, the other bulbs. Uh, yep, burn the same as before. Same as before. Right here. Uh, take a look at this. Switch the screen here. Right, right. So, like if this bulb burns out, right, these other guys still have the same voltage across them. Right. So if you're going from like the pink plane to the green plane, right, same voltage. That's like a so many volt battery. Do you guys remember too when Paul Hewitt was constructing this with one bulb at a time? Okay, put on one bulb, it lit up some brightness. You put on a second bulb, what happened to the brightness of the first one? Stayed the same. And the third bulb, right? The other two stayed equally bright as they did before, right? They each have the same voltage drop going across them. Oh yeah, yeah. Okay. Right. So then now if you start removing bulbs, well, the others are again not going to change what they're doing. They still have the same voltage going across them. Kahoot King on fire to the top. In a simple parallel circuit. Ooh, okay. Thought you guys gonna get that. So, thought you guys did. The voltage drop is always the same in parallel, but the current not necessarily. Uh, so switch over. Okay. Right, so do here two slides. I'll show you guys that's going to back that up. All right. So one is here. Okay. So now if these are all the same resistor, if they're like same number of ohms, then the voltage drop would be the same, but the current would also be the same for each one. Right. Kind of like if you're driving around town, right? I see like five traffic lights there, five there, five there. Right? It's all equally appealing paths. Right. Uh, what if you increase the resistance of one of these? What if you have like 10 traffic lights on this street, right? And only five and five here, right? Well, now probably not too many cars want to take the path with 10 traffic lights. They'd rather do the ones with fewer traffic lights, right? So now that's a difference in current, but not a difference in voltage, right? Notice these always in parallel, they're always the same voltage drop, right? So if one of these has a huge resistance, what that would equate to in the waterfall model is I have a little skinny waterfall with hardly any current in it, right? But they're all the same voltage drop. Guess that. And the other slide I can show you guys to back that up are these Kirchhoff rules. I did redesign the slide because maybe it's kind of overkill explanation, but Kirchhoff really only had two rules. He had this loop rule, which actually applies to anything, series or parallel. He had this junction rule right here, right? But all these other rules kind of fall out of those. Right? So let's look at this one right here, right? This is what you were just asked. So in a parallel setup, the voltage drop is the same across each one, even if they're different resistors, even if it's like 5 ohms and 50 ohms, that matters, the same voltage drop. Okay. Let's go there. Okay. And that is actually consistent with the loop rule also. The loop rule. All right. So loop rule type question. All right. Back to the top. In a simple parallel circuit, all right, nice. Yeah, all those statements are true. Right. Let's go through those. It's got a simple parallel setup right here. Okay. So the voltage drop has to be the same across each one, and even if they're different resistors, this is always true, consistent with that loop rule. Okay. Oh yeah, thank you, John. The current will divvy, right? Actually, it has to be conserved overall, right? So if it's like 10 amps coming in, it might split 3 amps and 7 amps, but it has to all equate, right? And the amount of current they said was inversely proportional to that particular resistor, right? And the way I wrote it here, like mathematically, you can say the current through like branch A is actually directly proportional to the resistor B. If you just have two resistors, you can do it that way. Okay. Right. Kind of like more traffic wants to flow through fewer stoplights, kind of deal. Here. Fuses and circuit breakers. All right, nice. All the above. Right. So once everybody got that, so let's just look at this real fast. Okay. You guys remember fuse right there? Right. So if there's too much current flowing, it'll blow the fuse, which will open the circuit and stop the current flowing. Okay. Ooh, let me ask you guys this. Do you want this fuse connected in series or parallel with the rest of your circuit? In series, exactly. It has to be series because if it was parallel, then there'd be another route for the electricity to flow and be completely pointless, right? Yeah. Right. So put your fuse in series. Astronaut 5 moving up, still on top. Short circuit occurs when yep, positive connected directly to the negative. Right. without a resistor, right? So if you don't have any resistance, right? Um, okay. So if you make a circuit without a resistor in it, connect positive directly to negative. Okay. Now you guys saw kind of a version of that. You guys remember the circuits page? Okay. This one right here, there was a short. Now this isn't exactly a short circuit because it doesn't connect the positive to the negative exactly. There are a couple of resistors there, but this wire does short out these two resistors, right? It shorts it out because there's no resistance on that path. So there's your entire circuit right there. Okay. What's that do? Two lamps. Uh, Thick filament and thin filament connected in series. The current is greater in the lamp with connected in series. Uh, all right. Yeah, it has to be the same current. Okay, so little trick question there. Sorry. Okay, let's look at this again. Remember, in a series, zoom out. There you go. Okay. Remember, in a series setup, right, the current is the same everywhere. Okay? So waterfall analogy could be like 3 gallons per minute, 3 gallons per minute, 3 gallons per minute. Okay? Even if these are different resistors, if they're different resistances, that just means that the voltage drops are going to be different. Right? But it's the same current everywhere. Okay? Let's look at the Kirchhoff. Well, that's a all right. Guys know this? In series, the current's the same everywhere, even if the resistors are different. All right, two lamps, thick filament, thin filament, connected in parallel. The voltage is greater across the lamp with the oh, nice, nice. Yeah, this is the same voltage drop. Right, you guys got that. Remind you guys real fast. This works. Right. So now thick filament, thin filament, that just means different resistances. Right? Thick filament has a small resistance, thin filament has a high resistance. But even if that's true, it's the same voltage drop. Okay? That's consistent with uh, this Kirchhoff rule right here. This is a version of the loop rule. Oh. All right. Two lamps, thick filament, thin filament, connected in parallel. The current is larger in the lamp with the thick filament. There you go. Because you guys remember that thick filament has less resistance. If there's less resistance, more current wants to divert that way, right? Would that be true? Right. In a parallel circuit. All right. Got how are we doing points? Got Scott, Hawthorne, Natalia, Gina, Ashlyn, and two lamps, thick filament, thin filament connected in series. The voltage is greater across the lamp with the Ooh, right. So you guys know the thin filament would have a greater resistance, right? Right. You guys good with that? So thin filament, greater resistance. Okay. Now, once you have that, then let's switch over to how does the voltage drop? Okay. So in series, so one after another. Okay. It's gonna be voltage drop here, voltage drop here. So maybe here, example numbers. Maybe it's like 10 volts from the battery. Maybe it drops like 7 volts and then 3 volts, for example, right? So you can drop a little bit at a time, but each voltage drop is going to be proportional to that resistance. So a thin filament would have a greater resistance, which would be a greater voltage drop. Okay. 70-watt bulb connected to a 12-volt car battery. Another 70-watt bulb connected in parallel. The battery's output energy. It would double. So if we're talking about a parallel setup, right? Let's go follow this right here. Okay. Let's take a look at this parallel setup. All right, parallel. Here we go, parallel, right? Okay. So, say we start off with just like one lamp here, right? So the current flows around, right? It's all fine and good, right? Then we open up there's the second route, so second resistor, second bulb, right? Okay. Now they each have the same voltage drop across them, right? So follow Ohm's law. I equals V over R. Where's Ohm's law? Let's find Ohm's law. Um, there's Ohm's law, right? Now they're each the same voltage drop, right? So some resistance, have more current flowing, right? So you'll have ooh, so you had like 5 amps here. Here's another 5 amps here. That's like double the overall current. And then Joule's law, power is current times voltage. Right? So if it's double the current, it's going to be double the power. So battery's being drained twice as fast. Total resistance of 9 ohms and 10 ohms in series is 19 ohms. There you go, because you just add them, right? 9 plus 10 is 19. That's good. All right. Total resistance of 4 ohms and 4 ohms in parallel. Two ohms. There you go. 4 and 4 in parallel is 2. Oh, here. Yeah. Write that one down. Okay. So here's resistors in parallel. So the previous question was resistors in series. You just very simply add them. Okay, so like 10 plus 9 was 19. Okay. The one here, resistors in parallel. Now you could use this reciprocal method. That's fine. If there's just 2 at a time, you could do product over sum. I got. Oh, and actually, we kind of got that here. So, but this was like 4 ohms and 4 ohms, right? Let's say resistance total is 4 times 4 over 4 plus 4. That's like 16 over 8. Okay. It's like 2, and then that would be ohms. Ohms is the unit, 2 ohms, right? Or if you're painting a fence, takes you 4 hours, takes your friend 4 hours by themselves. Team up. I can knock out the job in 2 hours. Same thing. Yeah. All right. Pick up. Current through 2 identical light bulbs connected in series is 1 amp. The voltage is 140 volts. What's the resistance of a single bulb All right, so 70 ohms. Ooh, I might need to do a little more time on that one, but okay. Yeah, you guys what I got. Okay. So here's two bulbs in series. Okay, connected to, I got 140 volts here. So 140 volts is the source. Okay. So here's Ohm's law, well, one version of it. Okay. Now this is the total resistance. So I can solve for R sub T. And that would have to be resistance total is 140 ohms. Is that okay? So each bulb, since they're identical, they're in series. So resistance of a single bulb must be 70 ohms. Is that so? 70 ohms, 70 ohms. Okay. Right. Or if you started by knowing what the resistances are, 70 70 in series makes 140 ohms. You got well, 140 volts divided by 140 ohms also gives you 1 amp. Right? Think of it that way. Okay. On fire. In order to make a flashlight bulb light up, all you need to do is run a wire from the positive terminal to the center of the bulb's base, true or false. Okay, so that is false because that would be an open circuit. Let's take a look at this flashlight schematic right here. Right? Okay, so see, if all you did was ran a wire from the positive terminal to the base of the battery, or sorry, the base of the bulb, I meant to say base of the bulb, right? That would be an open circuit. Okay? You need a complete path. You need also for the current to be able to flow all the way back to the negative terminal into the battery, right? Uh, Bulbs connected in series all carry the same current. Yep, that is true. Oh, everybody got it. Nice, nice, nice. Okay. So just for anybody watching this video at home, it's a refresher. We're talking about this rule right here. The current's the same everywhere in series. Same current everywhere. Same number of amps. Right? Even if they're different resistances, still true. In a series circuit, the total voltage drop across a series of resistors is the sum of the voltage drops across each individual resistor. True, true. Right, nice. So, remind you guys where you've seen this. Okay. So, in my waterfall analogy, right, we got battery pumps up some number of volts, right? And there's drop, drop, drop. So voltage drops. But if you add up these three voltage drops, it adds up to the same as the battery pumped up in the first place. Okay. And conventional physics textbook explanation is called the loop rule. That's also called the loop rule. Okay. In a parallel circuit, current in each branch is the same. Oh, okay. So why is that false? Let me skip back over here. Let's look at a parallel setup. Okay. So you have resistors in parallel. Okay. The current's going to split, right? Okay, so the current's going to split. Okay. Now, how does the current split? Well, it's proportional to the opposite resistor. Okay. So if there's like 3 ohms here and 7 ohms here, I bet 7 amps wants to go through 3 ohms and 3 amps wants to go through 7 ohms, if it's like 10 amps supplied, something like that. Okay. Now the current could split evenly only if the resistors are the same, but that's not universally true. Okay? Only if resistors are different, then the current's going to split differently. Everybody okay so far with all these? You good? All right. Got in the lead on fire. 2 questions left. A schematic diagram is a simplified, blocked out picture of a circuit, which all parts of the circuit are represented by symbols. Boom, true. Okay, so real fast. Let's look at an example schematic. Okay. There's the flashlight on the bottom and the schematic equivalent on top. There you go. There. Still on fire in the lead. When resistors are arranged in parallel, their overall resistance is less than that of the smallest resistor. True. Okay. Now, why would that be exactly? Okay, so take a look. Okay, so, where's that's not page I want exactly. Let me find where's resistors in parallel. There we go, resistors in parallel. Okay. So you guys know every time you add on a resistor in parallel, the overall resistance decreases, right? Just like every time you add on a team member, right? The time to finish the job decreases. Same idea, right? Same math. Okay. But what about the whole deal about like the smallest resistor? What's that about? Well, let's think of some numbers here. What if this was like 1 ohm? This guy's like 100 ohms, and this guy's 100 ohms. Wow, 1 ohm, 100 ohms, 100 ohms. Would you guys really believe that the total resistance is less than 1 ohm? Right? Well, hey, what if we just change the story out with something that's analogous? What if it takes this guy 1 hour to paint a fence, this guy 100 hours, and this guy 100 hours, then make a 3-man team, right? Do you think the overall time would it would be a little bit less than an hour, wouldn't it? Right? Maybe not much, maybe like 59 minutes and something, but these guys aren't going to do very much. But yeah, it would be less than the smallest time. Right? And replace painting a fence with circuit, resistors, boom, same story. Okay, so if there's like 1 ohm, 100 ohms, 100 ohms, the overall resistance would in fact be a little bit less than 1 ohm. Okay? Not much less, but a little bit. In order to prevent overloading in a circuit, fuses are inserted into the circuit. True. Nice, nice, nice. True. And finally, we got for the win, for the win. A fuse or circuit breaker is usually inserted in parallel, true, or false. False. Yeah. Way to go. You want that in series. All right, let's look at that real fast, and then we'll head over to the winner's podium. Okay. So fuse, see how it's in series with everything else, which is exactly what it should be in series. Too much current, it's going to break the fuse and then blow the fuse and stop the current flow. All right. To the podium. With the bronze. Hey, dude. Hello. The silver. Gina. And the gold. Oh, all right. All right, got runners up, Ashland and Scarlett. All right. So yeah, hang on to that packet, and then that is a wrap on today.